2011, the International Standards Organization released the first functional safety standard to the automotive industry with the purpose of reducing risk in electrical and electronic systems. ISO 26262 was adapted from an existing safety standard, IEC 61508, to address the specific needs of these systems within road vehicles. The term hazard is defined in this standard as a potential source of harm caused by malfunctioning behavior of the item in question. Semiconductors are a key component of any electric system in a vehicle and are subject to malfunctioning due to a variety of causes. These so-called random hardware faults, if not addressed, can lead to a failure and a hazard occurring. To mitigate these failures, safety mechanisms can be implemented so that the fault does not lead to a hazard, but instead leads to a known, controlled, and most importantly, safe state of the system. Two metrics have been defined for gauging the risk of a hazard due to a fault in the item. A single-point fault is not detected by a safety mechanism and alone can lead to failure. A latent fault is a multiple-point fault whose presence is not detected by a safety mechanism and can lead to failure. These metrics, SPFM and LFM, are used to assess the effectiveness of the hardware architecture with respect to safety. The term item is used in ISO 26262 to indicate a system or array of systems that implements a function or part of the function at the vehicle level. Complying with the standard requires that independently the item can be proven to meet defined targets for these two metrics. Certain challenges are faced by the supplier and the integrator in order to achieve compliance. This is the motivation for the usage of an analysis tool, one that can be customized to address these challenges. By considering a component as an item, the customizable analysis report from Renesas, or CAR tool, provides a base analysis approach looking at the characteristics of the component only. A golden database of the component is provided with a high degree of customization for different application profiles. In the CAR tool, the architecture of the component, a microcontroller in this case, is sufficiently divided for in-depth safety analysis, including those circuits required for intended operation as well as those dedicated as safety mechanisms. Let's focus on one element of the component and the safety mechanism used to mitigate potential failures of the element. Memory on the device, such as RAM, is used to store safety-related data and executable code. A single bit flipped in any one of these memories could result in a hazard and must be protected. All memories of the device should be protected with ECC, or error correction code, which is a safety mechanism that provides a method for single-bit faults to be corrected and normal operation to continue. Memories are constructed in silicon as an array or matrix configuration. In the hardware description, we will filter on matrix to locate these memories in the CAR tool. Note that the fault characterization for all memory matrices are identical. We will transition to the fault characterization information for a closer look. The fault characterization for the memory matrix for the technology used in this device consists of two potential failure modes: single-bit failures and 2-bit failures. The distribution of these failure modes is defined as well. The fault impact for each failure mode can be analyzed independently. ECC has been assigned as the safety mechanism for each memory matrix, and the fault coverage for single-bit failures is assigned based on ECC standard practices. 100% coverage can be achieved for this specific failure mode. From here, the user can transition to analysis results to see the contribution of ECC to the target metrics. For each memory matrix, the fault coverage is realized at 100%. Therefore, the resulting SPFM and LFM can achieve 100. By expanding the results to include all elements, the metric achievement can be seen for each element individually. In addition to calculating and reading the Renesas analysis results of the device, the CAR tool allows the integrator to customize each and every aspect of the analysis based on the required context. Compare results, combining fit rates from different sources. Revise safety-related status for each element of the component. Evaluate results against different safety goals and timing constraints. Enable and disable safety mechanisms. Add system-level safety mechanisms. Change fault characterization. Revise fault impact and revise fault coverage. All of this makes Renesas CAR tool the safety analysis tool of choice for an accurate, unified, and cohesive analysis of an item or system with the flexibility of customization for any application context.